Alarm Management, a white paper. Overview of alarm philosophy and process safety. Alarm systems are foundational to safe and efficient plant operation, serving as the operator's primary interface with abnormal conditions. However, when alarm systems are overloaded or poorly designed, they can hinder rather than help. Excessive numbers of alarms, especially nuisance, standing, or repeating alarms, lead to cognitive overload, increase operator stress, and mask critical information behind floods of low-value alerts. Incident investigations across various industries have demonstrated that alarm floods have been significant contributors to operational failures and disasters. In response, the UK's Health and Safety Executive, HSE, ranks alarm system design among its top safety priorities. While there is no universally binding standard, the EEUA 191 guidelines have become the de facto reference for defining acceptable and effective alarm management practices. Alarm systems are not static engineering artifacts. They must be designed, implemented, and maintained according to rigorous principles that balance safety, clarity, and operator actionability. An effective alarm is not one that merely signals a deviation, but one that provides a meaningful prompt for timely operator intervention. Achieving this requires a life cycle approach, from initial configuration through rationalization, verification, and continuous review. The application of EU-aligned practices allows organizations to address alarm system issues systematically, improving both operational integrity and human reliability across a range of industries, from oil and gas to utilities and transport systems. Human factors and the alarm response interface. In modern automated environments, process operators typically spend long periods in a passive supervisory mode monitoring systems that operate largely without intervention. However, when deviations occur, the transition from routine observation to crisis management is often instantaneous and overwhelming. One operator aptly described it as a shift from boredom to panic in a couple of seconds. This sudden escalation is typically accompanied by multiple simultaneous alerts, buzzers, klaxons, flashing indicators, and console messages, all demanding immediate attention. Humans are inherently limited in their ability to process large volumes of information under pressure. Studies suggest that operators can reliably handle 2 alarms per minute with short-term spikes of 4 to 5 alarms per minute at most. When these thresholds are exceeded, operator performance degrades significantly. The immediate consequence is reduced alarm recognition and slower or incorrect response. More dangerously, operators often transition into action mode, where they commit to an initial diagnosis and rarely reassess it, even when conflicting information arises. This phenomenon, known as confirmation bias under stress, has been a root cause in notable aviation and industrial accidents. Alarm systems, therefore, must be designed not just with technical accuracy, but with cognitive ergonomics in mind. Ensuring that alarms are prioritized, actionable, and free from clutter is not optional. It is essential for enabling sound operator decisions in the face of abnormal situations. Boredom to panic, the cognitive challenge of alarm response. In modern automated process environments, operators often spend extended periods in a passive monitoring state, observing systems that function reliably with minimal need for intervention. During such steady-state operation, human engagement tends to be low, with operators becoming accustomed to stability and predictability. However, when a deviation or fault occurs, the transition to abnormal conditions can happen almost instantaneously, turning a calm situation into a high-pressure event within seconds. This rapid shift is frequently accompanied by a cascade of alarms, audible alerts, flashing lights, and system messages all demanding simultaneous attention. This flood of sensory inputs exceeds what operators can effectively process under time constraints, leading to cognitive overload. The human brain can only process a limited number of stimuli at once, and when alarm rates exceed manageable thresholds, critical signals may be missed or misinterpreted. Operators may begin acknowledging alarms reflexively without fully analyzing the situation, undermining the alarm system's purpose. Compounding the issue is a psychological shift that occurs under stress. As alarms increase, operators tend to transition quickly from observation to action, committing to an early diagnosis and acting upon it. Once in this mode, reassessment becomes unlikely, even if new information suggests the initial response was incorrect. This behavior, driven by urgency and pressure, can escalate minor disturbances into major operational incidents. Effective alarm system design must therefore anticipate human limitations. It should present alarms in a manageable, prioritized manner, ensuring clarity, reducing clutter, and supporting deliberate operator response. By aligning alarm behavior with human cognitive capacity, the system becomes a tool for stability rather than a source of confusion during critical moments. Three alarming problems: structural weaknesses in alarm system design. Alarm systems in industrial operations are often compromised by three persistent and interrelated problems: standing alarms, nuisance alarms, and alarm floods. Each of these conditions diminishes the system's effectiveness, increases cognitive burden on operators, and undermines the integrity of control room decision making. Standing alarms are alerts that remain active even when the plant is operating normally. These are frequently the result of faulty instrumentation, inappropriate alarm thresholds, or equipment that has been taken out of service. While they may not generate constant attention, their presence renders the alarm point effectively useless. If a true deviation occurs on that point, the system is already in an alarm state and cannot signal a new condition. Over time, operators may begin to ignore or mentally filter out standing alarms, which desensitizes them to both real and critical alerts elsewhere in the system. Nuisance and repeating alarms occur when alarm points continuously toggle between active and cleared states. These are commonly caused by poor alarm limit settings, a lack of hysteresis or deadband control, or unfiltered instrument noise. During process upsets, such alarms become especially problematic, contributing to alarm floods and drawing attention away from more serious events. Their repetitive nature distracts operators, increases stress levels, and degrades situational awareness. Alarm floods are the most dangerous of the three issues. In the event of a disturbance or plant upset, hundreds of alarms can be generated within minutes. This overwhelms operators, forcing them to acknowledge alarms without evaluation, and often resulting in critical messages being missed. The volume and speed of incoming alarms during a flood effectively collapse the operator's ability to prioritize or diagnose the root cause of the issue. Together, these three alarm problems compromise the reliability of the entire alarm system. Addressing them requires not only technical adjustments, such as instrumentation fixes, revised alarm thresholds, or logic changes, but also a sustained operational discipline to review, rationalize, and continuously improve the alarm configuration. An optimized alarm system is not just quieter, it is smarter, clearer, and more responsive to actual risk. Why so many alarms? The accumulation problem in system design. Modern industrial facilities often deploy thousands of alarms across their control systems, far exceeding what operators can manage during normal or upset conditions. While each alarm may have been added with good intent, typically to signal deviation, risk, or equipment status, the cumulative effect creates a system that is overloaded, noisy, and inefficient. This problem often begins at the design stage. When reviewing a small portion of a plant, adding a few alarms appears to enhance safety and control. Engineers aiming to be thorough may include alarms for every conceivable deviation or fault. However, when this approach is applied across an entire facility, the result is exponential. Thousands of alarms, many redundant or of marginal value. The logic that supports a few additional alarms in isolation collapses when applied system-wide. In many cases, alarms are added without rigorous review or formal justification. The cost and effort of questioning their necessity often outweigh the ease of simply including them. This leads to a scenario where the alarm system becomes dense with low priority or duplicate alerts that contribute little to operational safety or decision making. The unintended outcome is a system where the signal-to-noise ratio is low. Important alarms compete with trivial ones, and during abnormal events, the volume of alarms increases dramatically, making it harder to isolate the root cause or prioritize corrective action. To mitigate this, alarm design must be approached holistically. Instead of focusing on alarm quantity, the emphasis should be on alarm quality, ensuring each one has a defined purpose, a required operator response, and contextual relevance. Alarm systems should be optimized, not accumulated, to truly support operational clarity and safety. New plants, designing alarm systems for prevention, not repair. The design phase of a new plant presents a unique opportunity to establish a clean, purpose built alarm system, free from the legacy issues and compromises that typically afflict mature operations. At this stage, alarm integrity is not a matter of remediation, but of deliberate design. The goal is to embed alarm quality, clarity, and discipline from the outset, making future operations smoother, safer, and less reactive. A foundational principle is this: an alarm that is never configured will never become a nuisance, a standing alarm, or a contributor to a flood. Therefore, restraint is critical. Alarm points must not be added by default or for speculative scenarios. Each proposed alarm should require a documented justification based on operational risk, along with a clearly defined operator response. If there is no actionable step the operator can take or no realistic time window in which to take it, the alarm does not belong in the system. Rather than relying on ad hoc decisions, alarm definition should be governed by a formal alarm philosophy document. This document outlines the plant's alarm management strategy, criteria for alarm inclusion, prioritization methodology, and operator interface principles. It ensures that all contributors, engineering, operations, and control system vendors, adhere to a shared vision of what constitutes a valuable alarm. Traditional safety reviews, such as HAZOP, often exacerbate the alarm quantity problem by treating each deviation individually and adding alarms as a precaution. Instead, alarm justification should consider the plant holistically, assessing whether the alarm enhances overall situational awareness or merely adds redundant noise. In some cases, it may be more appropriate to address safety concerns through control logic, automated trips, or process design, not alarms. Finally, new plants should be commissioned with a mechanism for performance feedback already in place. This includes alarm event historians, configuration audits, and baseline metrics to support continuous improvement. The alarm system should not be considered complete at startup, but rather initialized with the expectation that it will be refined as operational experience accumulates. A disciplined alarm design for new plants establishes a framework of reliability and human-centered performance. By preventing problems at the source, the system becomes not just a diagnostic tool, but an enabler of resilient, high-quality operations. Existing operations, restoring alarm system integrity through structured intervention. In established facilities, alarm systems often evolve without consistent oversight, resulting in bloated configurations filled with redundant, irrelevant, or malfunctioning alerts. What may have started as a well-intentioned design deteriorates over time due to equipment changes, process modifications, rushed projects, or operator workarounds. The outcome is an alarm environment that overwhelms rather than assists, undermining both safety and operational confidence. Revitalizing an existing alarm system requires more than superficial tuning. It demands a structured, data-driven, and policy-anchored approach. The first step is assessment, gaining visibility into the system's current state. This includes auditing the total number of configured alarms, their assigned priorities, the volume of standing and repeating alarms, and alarm rates during normal operation and process upsets. Most modern control systems support alarm historians and diagnostic tools, which can provide invaluable insight into real alarm performance. With a clear performance baseline in hand, the next phase is rationalization. This involves systematically reviewing each alarm against a set of core principles. Does the alarm prompt an operator action? Is that action time sensitive? What are the consequences if the alarm is missed or ignored? Alarms that fail these tests should be downgraded, suppressed conditionally, or removed entirely. Duplicate alarms, those tied to normal transitions, or alarms on out-of-service equipment, must be eliminated or dynamically managed. This process must be guided by a formal alarm philosophy document, a central reference that defines alarm purpose, configuration standards, prioritization rules, and acceptable load thresholds. Without such a standard, rationalization becomes subjective and inconsistent, leading to regression over time. The improvement effort should also consider operational realities, such as shift patterns, control room ergonomics, and the robustness of automation. Alarm system quality is not defined by configuration alone, but by how effectively it supports human decision-making under stress. Most importantly, Alarm improvement is not a one-time exercise. A continuous review loop must be established where alarm statistics are collected, performance trends are analyzed, and configuration changes are governed by a change management process. This ensures that gains are sustained and that the system continues to reflect the evolving needs of the operation. In summary, transforming existing alarm systems is entirely achievable with the right structure, persistence, and leadership. The result is a cleaner, clearer, and more trusted interface between the plant and its operators. Alarm rationalization, transforming alarm systems from noise to value. Alarm rationalization is the critical process of converting an overloaded, inconsistent alarm system into a streamlined, purposeful tool that supports timely and accurate operator action. In many facilities, alarm configurations grow unchecked, resulting in duplication, misprioritization, and false urgency. Rationalization is not simply about reducing numbers, it's about elevating signal quality and ensuring that every alarm serves a clearly defined operational role. The foundation of effective rationalization lies in asking two key questions for every alarm. 1. Is operator action required? 2. Is there a defined time window in which to act? If the answer to either is no, the alarm may not belong in the system. From these principles, several design rules follow. Eliminate duplicate or redundant alarms. Do not alarm expected or routine events, e.g. startup transitions. Avoid alarming operator-initiated actions. Limit each protective function to one relevant pre-alarm or warning. Priority assignment is equally important. Alarm overload often stems not from the number of alarms alone, but from the misclassification of their urgency. High-priority alarms must be rare and genuinely critical. A well-rationalized system might allocate no more than 10% of alarms at high priority, 20% at medium, and the rest at low, ensuring that urgency correlates with actual operational risk. To guide this process, many plants adopt a risk-based prioritization methodology, assessing alarms based on potential consequences to safety, environment, equipment, or production, available operator response time, and the probability of occurrence. This approach mirrors methodologies used for safety instrumented functions and enforces consistency across systems. Rationalization also serves as the interface between alarm system integrity and human factors. It ensures that alarms are manageable in volume, clear in meaning, and aligned with how operators think and respond during stress. Ergonomic considerations, interface design, and diagnostic context must be included as part of this process to support effective decision-making under pressure. Ultimately, alarm rationalization is both a cleanup and a design exercise. It brings discipline to alarm configuration, filters out noise, and restores trust in the system. When properly executed, it transforms the alarm layer from a reactive hindrance to a proactive safeguard, focused, effective, and aligned with the reality of control room operation. Basic principles: establishing the foundation of an effective alarm system. At the core of any well-functioning alarm system is a clear, disciplined set of basic principles. These principles act as the gatekeepers, ensuring that only meaningful, actionable, and necessary alarms are included in the system. Without such a foundation, alarm configurations tend to grow indiscriminately, leading to overload, operator fatigue, and ultimately compromised safety. The first and most essential rule is purpose. Every alarm must exist for a reason. That reason must be tied directly to operator action. An alarm that does not demand a response, or one for which no meaningful action can be taken within the time available, has no operational value and should not be configured. From this core principle, several guiding rules emerge. No alarm without action. Each alarm should be linked to a defined operator response. If the system provides information only, consider trends or logs instead. Eliminate duplicates. Multiple alarms for the same condition, e.g. flow low and valve closed, create confusion and dilute urgency. Consolidation is key. Avoid alarming the expected. Do not configure alarms for routine events like startups, transitions, or operator-initiated changes. These only serve to distract during already busy periods. Limit pre-alarms. A single, well-placed pre-alarm is often sufficient. Stacking multiple early warnings for the same risk only adds noise. Control prioritization. Not all alarms are equal. The number of high-priority alarms must be tightly limited to ensure that true emergencies stand out clearly. Priority must reflect consequence and urgency, not subjective importance. Design for clarity. Alarm messages should be concise, unambiguous, and descriptive enough for the operator to understand the issue and act without delay. Adherence to these principles creates a structured, reliable alarm system that acts as an operational asset rather than a liability. It ensures that alarms function as intended, not simply to notify, but to guide, protect, and support human performance under pressure. Without these foundational rules, no amount of advanced logic or system sophistication can make an alarm system truly effective. Risk-based methodology, aligning alarm priority with operational impact. A risk-based methodology brings structure and objectivity to alarm prioritization. Rather than assigning priority based on intuition or habit, this approach evaluates each alarm according to its real-world consequences, the operator's ability to respond, and the urgency of the situation. It ensures that alarms are not only technically correct, but operationally meaningful. At its core, the risk-based method asks three fundamental questions for each alarm. 1. Can the operator take meaningful action? 2. Is there sufficient time to respond effectively? 3. What are the consequences if the operator fails to act? These questions shift the focus from what the system detects to what matters in practice. An alarm that sounds during a non-critical event but leads to no operator intervention has low operational value and should not be prioritized. Conversely, an alarm that signals a condition with potential for equipment damage, environmental release, or production loss and allows the operator a window for corrective action justifies higher priority. Consequences are typically grouped into four risk domains: personnel safety, environmental impact, equipment integrity, production continuity. The likelihood and severity of the outcome, combined with the available response time, determine the alarm's criticality. For instance, an alarm with a severe outcome but no time for intervention does not serve the operator. It may be more appropriate as part of an automatic shutdown system rather than an audible alert. By embedding these risk criteria into the alarm design process, the system achieves consistency across units, shifts, and contributors. It also enables rational limits on high and medium priority alarms, preserving operator attention for what truly matters. Alarms with low risk or delayed consequences can be demoted, delayed, or even removed from the active set. A risk-based approach does more than sort alarms. It restores their meaning. It ensures that each alert reflects not just a system state, but a real operational threat that warrants human awareness and response. In doing so, it transforms the alarm layer into a strategic component of plant safety and reliability. Ergonomics and operability, designing alarms for human performance. An alarm system is only as effective as the operator's ability to perceive, interpret, and act on its signals, especially under pressure. While much of alarm design focuses on logic and configuration, ergonomics and operability determine whether the system works in practice. These factors influence how operators interact with alarms, how quickly they understand the situation, and how confidently they can respond. Ergonomics addresses the physical and cognitive aspects of alarm delivery, how information is presented, how clearly it's understood, and how easily actions can be taken. Poorly designed alarm interfaces, cluttered screens, ambiguous messages, inconsistent colors or sounds can overload the operator's senses and slow down response time. Alarm messages should be concise, context-rich, and instantly recognizable. Visual hierarchies, grouping strategies, and color coding must be intuitive and consistently applied across all displays. Operability, on the other hand, concerns the broader system environment, the interaction between the operator, the control system, and the process. A robust alarm system must work hand in hand with reliable automation, well-tuned loops, and clearly defined process responses. If the basic control logic is unstable or if routine actions generate alarm traffic, the operator's trust in the alarm system erodes. This leads to alarm fatigue and eventually disengagement. Both ergonomics and operability must be considered during system design and reviewed during rationalization. Key practices include optimizing screen layout to reduce eye movement and improve scanning, avoiding visual clutter by grouping related alarms and suppressing inactive elements, designing for context so that alarms appear within process diagrams, not detached lists. ensuring consistency in message format, priority indicators, and alarm tones. Aligning alarms with automation behavior, so operator expectations match actual plant responses. Ultimately, an alarm system should guide the operator, not overwhelm them. It should act as a real-time decision support tool, delivering the right information at the right moment in the right way. When ergonomics and operability are prioritized, the alarm system becomes a reliable partner in maintaining situational awareness, even under the most demanding conditions. Tools and techniques, managing alarm volume with structured strategies. One of the most persistent challenges in alarm management is sheer volume. Industrial systems often contain thousands of configured alarms, many of which offer little operational value. Reviewing each one individually is not only time-consuming but also impractical, especially in large mature facilities. To regain control, alarm volume must be addressed through structured, scalable techniques that focus on pattern recognition, categorization, and automation. A powerful first step is categorization. Instead of evaluating alarms one by one, alarms are grouped into logical types, such as trip pre-alarms, equipment failure indicators, process off-spec, or diagnostic alerts. Each category can then be assigned consistent priority rules, message formatting, and suppression logic. This accelerates rationalization while maintaining alignment with plant risk philosophy. Exceptions can be handled case by case, but the bulk of alarms benefit from standardized treatment. Another effective tactic is alarm grouping, particularly for systems with repetitive structures like pump skids, compressors, or packaged units. Here, individual input conditions are logged but not alarmed directly. Instead, they are logically combined to trigger a common group alarm, e.g., compressor skid fault, which directs the operator to a more detailed status display. This reduces alarm noise without losing traceability. When implemented with first-up logic, the root cause of the group alarm is flagged clearly, allowing quick diagnosis and prioritization. Dynamic suppression further enhances control. Using predefined logic, alarms can be temporarily disabled based on operating mode, process condition, or state transitions. For example, alarms from a pump can be masked when it is out of service, or delay timers can be applied after startup to prevent flooding. These techniques ensure alarms are relevant to the current context and not triggered by expected behaviors. Crucially, these tools must be underpinned by proper software infrastructure. Alarm analysis tools, such as spreadsheet-based evaluators or specialized databases, support efficient sorting, flagging, and bulk edits. Control system features like historian integration, event trending, and suppression status monitoring provide the transparency needed to tune and validate configurations over time. Dealing with volume isn't about eliminating alarms, it's about creating structure. By categorizing, grouping, suppressing, and automating wisely, facilities can reduce clutter, highlight real risk, and empower operators to act with clarity and confidence. Tools and techniques, alarm reduction for a focused, actionable system. Alarm reduction is not about silencing the system, it's about refining it. In many facilities, excessive alarms arise not from equipment complexity, but from poor configuration, duplicated logic, or failure to suppress predictable events. The result is an alarm environment where operators struggle to distinguish between what is urgent and what is merely informative. Alarm reduction strategies aim to strip away the noise, leaving behind only alarms that truly require attention and action. One of the most effective methods is alarm grouping. When multiple inputs are likely to trigger during the same fault condition, such as a machinery failure, process trip, or utility loss, these can be consolidated into a single group alarm. The group provides a high-level notification, while detailed status displays offer diagnostic visibility. This technique is particularly useful in packaged equipment and skid-based systems, where local logic can generate cascades of similar alarms. Grouping reduces operator load while preserving access to root cause data. First-up logic enhances the grouping concept by identifying and highlighting the initial trigger among several contributing signals. When a group alarm is activated, the first variable to enter the alarm state is marked distinctly, helping the operator pinpoint the initiating fault. Once resolved, the first up can be reset to monitor for new events. This logic improves situational clarity, especially during fast-moving upsets. Another essential technique is dynamic suppression, which ensures that alarms only activate when they are meaningful. This includes out-of-service suppression, disabling alarms on offline or maintained equipment. Transient suppression, temporarily blocking alarms immediately after a known event, e.g., a pump start. Consequential suppression, muting follow-up alarms triggered by a known root event to avoid alarm flooding. These suppression methods reduce alarm clutter while maintaining auditability and system transparency. Suppressed alarms remain logged and visible in supporting displays, but do not compete for operator attention in real time. Basic control enhancements also play a role. Applying dead bands, delay timers, and hysteresis to alarm points reduces chatter caused by signal noise or frequent cycling near alarm thresholds. These small adjustments prevent nuisance alarms and build operator confidence in alarm reliability. Ultimately, alarm reduction is not about removing alarms, it's about refining them to serve a clear purpose. Through grouping, first-up logic, suppression strategies, and basic control tuning, alarm systems can be transformed from chaotic streams into structured, actionable guidance. The result is a cleaner interface, reduced cognitive burden, and faster, more effective operator response. For the long term, sustaining alarm system performance through lifecycle discipline. Building an effective alarm system is only the beginning. Sustaining its performance over time is what defines long-term success. Alarm quality naturally degrades without structured oversight as plant changes, instrumentation updates, and operational pressures introduce drift into the configuration. What was once a clean, rational system can quickly become cluttered with obsolete, redundant, or misprioritized alarms. To avoid this erosion, alarm management must transition from a one-time project to an embedded operational discipline. This involves creating a long-term governance model supported by ownership, tools, and accountability. Alarm metrics should be treated as core performance indicators, monitored, analyzed, and acted upon, just like process safety or production KPIs. A comprehensive alarm performance monitoring framework should include daily and weekly alarm rate tracking, average and peak values, identification of standing, repeating, and chattering alarms, top offender analysis by frequency and priority, monitoring of suppression usage and overrides. The control system or external software tools can automate much of this data collection, enabling efficient review without consuming operations bandwidth. What matters most is acting on the findings. Each trend, outlier, or recurring nuisance alarm should trigger structured follow-up, be it reconfiguration, maintenance intervention, or logic redesign. Strive for continuous improvement, making alarm quality a culture, not a task. Sustained alarm system health depends on an organizational mindset that views alarms not as fixed assets, but as evolving tools. Continuous improvement means constantly questioning whether each alarm still serves its purpose, whether priority levels reflect true risk, and whether operators are benefiting from or burdened by the current configuration. Key practices include routine alarm reviews during shift handovers or control room audits, change control integration, where new alarms or logic modifications are evaluated against alarm philosophy standards, feedback loops from operators, who experience firsthand which alarms are helpful and which are noise. Training programs ensuring that engineers and technicians understand alarm design principles and the reasons behind rationalization decisions. Improvement should be iterative, not reactive. A small, well-maintained backlog of alarm improvement actions, managed like maintenance work orders, keeps progress ongoing and visible. Over time, this reinforces a culture where alarm quality is not a one-off cleanup, but a continuous commitment to operational clarity and safety. When alarm systems are maintained with long-term intent, they remain reliable, trusted, and aligned with evolving plant realities. The result is not just fewer alarms, but smarter, safer, and more operator-friendly control environments.